Hello. The last time I used a number of different languages and tools, and that got quite complicated to present. This time, however, I've gone the other extreme. I'm just going to use Rider, and I've got everything in here, so hence my high quality slides. When Kevin asked me to do the talk, I agreed and I had a definite topic in mind. However, as I researched the talk, it sent me on a bit of a journey and I got a bit sidetracked. And tonight is a story of that journey. Right, so if you Google what has the best performance, a for loop or a for each loop in JavaScript, you get loads of results telling you that for each is really slow and for loops are much quicker. So this is what I mean by for loop and a for each loop. And so the question I was asking myself is this also true in C#? Now normally we don't care because loops are really, really fast and most of the time it really doesn't matter at all. But when you're doing things such as advent of code, you're trying to gain every single possible second you can so you can beat those Rust developers. With that in mind, I decided I was going to test it to work out which of the two approaches is in fact quicker. When you're timing stuff in .NET, when you're timing sort of really, really fast pieces of code such as this, you can't just use a normal stopwatch or a timer or datetime.now. You need something with a lot more precision because it has to take into account other things that are going on your laptop whilst you're testing your code. And so in order to reduce that noise when coming up with the timings. And the library, which is a great library, which a lot of people use, is benchmark.net. I'm also using another tool called Benchly, which allows you to create graphs from your results. So it's all configured using attributes. In this case, I've got the column chart attribute that says at the end I'm going to generate a column chart with this title. And also all my results have to return the same number. So if I'm running 6 different tests, all those 6 tests have to return the same value. If one of them returns a different value, then I say the timings are irrelevant because the tests aren't doing the correct thing. In order to time a loop, we have to actually give it some work to do, otherwise there's nothing to time. So for my test, I'm going to create an array of 10,000 numbers, so 0 to 99999, and then I'm going to try adding up these numbers. It doesn't really matter what the numbers are, in this case they are consecutive numbers. The first approach I'm going to use is a basic for loop. So you can see I'm going to use a for loop over the whole array, summing into a local variable called total where I return that at the end. Note that I've marked up the test with an attribute called benchmark, so the benchmark.net knows this is one of our tests. And also I've said it's the baseline test. So any other test I run is going to be compared against this one. So it'd say something like, this is 50% slower to run than the baseline. Another example, or another test I've got, is the for each, so the opposite one. So these are the two things we're comparing. So this time I'm just using the for each over the whole array. So that's pretty much what you need to do to set up the test. And normally you put something in program.cs as well to say this is what I'm going to run when my program starts up. The next important point is when you do your test, you have to build and run it in release mode. The easiest way to do that is you do .NET run -c release, and then it will go off, build your code, and then start running all the tests. Now I'm not going to run them now because it takes a few seconds to run, and it's quite a short talk. So fortunately, I've run the test earlier, and I've extracted the graph which you generated. And here we go. And a few things to note: I've removed the numbers from the graph because we're really interested in just comparing the different approaches at the moment. And we can see the for each loop is quicker than the for loop, which may come as a bit of a surprise to you because if you think about it, a for loop is just iterating over all the elements in an array, which we've always been told is really fast to do iterations over consecutive or contiguous areas of memory. So why is it that that's slower than the for each loop? Well, .NET must be doing something here in order to make this approach quicker than this one. And so, we'd like to know what that thing is. Now, as most of you are aware, the way the source code gets ran in C# is we have our source code, our C sharp. It then gets lowered to another form of C sharp. So this is where it gets rewritten. It removes some of the syntactic sugar and just comes up with a simpler form of C sharp. That C sharp is then converted into IL, and that IL is then converted into the assembly language that's going to run on your machine, on your processor. So one of these stages here is going to be hold the key as to why the for each loop is quicker than the for loop. So we can look at the IL quite easily using the IL viewer, which comes as part of Rider. He says if the window would open. Okay. And here we can choose up here what we're seeing, so we can see our IL code here, which is generated, and it's a stack-based language. To make it easier, what I've done is I've extracted the IL for both the two methods, and we can then put them side by side. We're going to need that again in a second. So, and okay, so this is our IL, and it's side by side, and we can see, well, yes, there are some differences. The for each one is slightly longer than the for loop. Maybe that's a clue, but it's all quite complicated, and so, you know, we could go off and we could look up each of these commands and work out what it means, but that's quite complicated, and I didn't really want to spend that much time. So I thought, well, where else can I look? Maybe the IL maybe the load C sharp might help. So we return back to our code. So we look at the high level C sharp first of all. You can see that's basically what we entered. It's replaced var with int, but other than that, it's the same. Okay, maybe the low level gives a clue. Well, that's quite interesting. The for each has actually been rewritten as a for loop, which is stranger still. So why is this now quicker than that? I mean, if anything, it seems to be doing more work. It seems to be taking a local pointer to the array and a local pointer to the value in the array. Okay, so that's maybe something to do with that, but it doesn't really make any sense. So the next thing maybe is, let's look at the assembly language. Now, reading the assembly language on an Apple Mac is actually quite hard. It's easier on Windows. The quickest approach is just to go to this website here, though, sharplab.io, paste in your C# code, and it will then show you the generated assembly language, which we can see here. Okay, so there's our two methods. We can see that the for loop is a lot more complicated than the for each. And the thing that stands out straight away to me was this call here, to core info help range check fail. And it's like, okay, so that's obviously something to do with that. And so a combination of that and what we're seeing with the lowered C# here, that's probably our clue. So I went off and I googled that command, and it comes up in a .NET performance improvements blog. I thought, well, this is great because it's bound to be looking in the right place now. And if we look at it, we can see it's all to do with range checking and making sure that when we access an element in the array, that we don't get an out of bounds, an element out of range error. So if we go back to our example, and okay, so maybe we can do another test now in that case. So we know it's something to do with ranges. So let's do our second experiment. So we've got the same basic tests as before, and we're going to add in a couple of extra ones as well. So we're going to try using a uint rather than an int. So an unsigned integer can't be a negative value. So does that mean it doesn't need to check the lower? It doesn't need to check that I is always greater than 0. It can't be sort of to the left of the array, as it were. And we can also see, well, maybe taking a local pointer to the array makes a difference, because that was the only real difference we could see. And if we run both of those, okay, we get our results. There's the first twos we had before. We can say using a uint makes no difference whatsoever. We can ignore that. But the local array is pretty much comparable now with our for each loop. So why is this? And the reason is the optimizer knows that because we've got a local array or a pointer to an array here, that can't ever change. So that's always fixed, the size of that. So up front, it's detected this pattern where I is always less than that. So it's detected that we're looping over an array, and you can optimize the checks away because this is such a common pattern. Now, it can't do it on the original version up here with this for loop because another thread could come along and change data whilst this loop is running. So it hasn't got that guarantee. But because we've got the local pointer to it, we know that's what it's going to be. Even if you run array.resize, that creates a new array and it will still keep this one in memory. So we know that this is going to be safe to the end of it. Okay, so that explains that, and we found a quicker way. That's great. So then I was thinking, well, this is probably the fastest we can do on a single processor, but we've obviously got quite a few processors in our computer. So yeah, maybe we should use some parallel processing and see if we can make it go a bit quicker. Now, this is the most naive possible solution, which we're not expecting to work particularly well, but it's something to get as a starting point, where we've replaced the for loop with a parallel.for, and then for each number, we just increment our total. Now, this code's not going to work because we've got a threading problem here. You can't have all the threads trying to update total at the same time. So we have to use interlock.add instead. And that means only one thread can be increment total at a time. And so we will then end up with the correct answer. Now, for completeness, we can also do the same thing with parallel.for each, and again, it uses interlock.add. We run this, which really takes a while, and we can see we get some very unimpressive results. The for loop is the original one, and now we've got the parallel versions are many times slower. But that's not really a surprise, because all we're doing is we've got this overhead of creating these extra threads, and each thread doesn't really do anything because they're all getting queued up behind this interlock.add. What we really want is to divide up the work between the threads. So this thread can do, say, 1,000 of the numbers, and then another thread do another 1,000. So we can do like 10 lots of 1,000 at once. So we can look at the code for that. Oops. So D41. So this is exactly what we do, is we take our data, we divide it up into a number of blocks. So we could say into 10 blocks, so each block would be 1,000. Then for each block, we just get the numbers in that range and add them up locally within the thread. So it's got a total of those, say 1,000, and then it puts its total into a concurrent bag, and then we return the sum of the bag. Okay, that seems like quite a better approach. So the question here is, how many blocks should we divide it up into? Well, this is something we don't know, but fortunately, benchmark.net has got another feature where parameters, where you can feed test parameters into your tests. So I can say, right, I'm going to run it for all these different block sizes. So I went off and I ran this, and this really does take a long time. And eventually you get a nice graph out. Unfortunately, the headings don't quite line up. But what we're saying here is if we've got one block, that's the fastest, and the more blocks we divide it up to, it's actually getting slower and slower. So the overhead of creating these parallel tasks or parallel threads is just too much. We don't get any gain at all. So parallelism isn't going to help us. But you have to remember here that in our loop, it's a really simple loop. We've got hardly any work going on. So in the real world, the real test, it will be a lot, you'll have a lot more gain from doing parallelism. Okay, does that mean that's it? There's nothing else we can do. We've got a fast for loop and parallelism doesn't work. Is there anything else we can try? Well, as it happened, so I said to ChatGPT, is there anything else I can try? And it came back and said, you can use unsafe.add, which you can access array elements without bound checks. I thought, great, that sounds exactly what I need, because that's sort of what we've been doing. So it's a for loop again, with some, using unsafe add. Maybe that's going to be quicker. What else can I do? I thought to myself, and I thought, well, spans. Spans are always quicker. Everyone says spans are for performance, so I can do, convert the array into a span and walk over that instead. So maybe that's going to be even faster. I can use pointers. Pointers are unsafe, and you can do anything, so they can't do any checking, can they? So that must be really quick. Or I could just get rid of the loop completely and just add together all the 10,000 values one at a time. Or I could do the opposite of that, and I could just use link and do it in one line. And so I went off and ran this, and a few seconds later, get our results. And the immediate thing we can see here is the unrolled one is much slower. So let's get rid of that from the graph so we can see everything else. Okay, so these are our first ones, our for each loops, our fastest version so far. Unsafe add, well, that wasn't particularly good. Span, that's helped. That brings it back down to this level. Pointer didn't help, but the surprising one is link. So link's actually a lot quicker than even our fast for each or our fast for loop, which is quite surprising. So it's like, okay, weren't we doing the quickest thing possible? We were iterating, over an array. How can it possibly be this much quicker? Okay, well, we need to do some investigation here. So if we drill into the sum method, you have to drill down a few times. And yeah, we get down to here. And then we start seeing things such as vector.is hardware supported and sum signed integers vectorized. And it's all looking a bit scary and complicated now. And there's a lot of code, you will notice. It's all this code here. And it's using these vectors and accumulators and so on. So what's this doing and how come it's so much quicker than just walking our array? So the reason is, when we're using the add command before, we can only add 2 numbers together at a time. Processors also have additional instructions which allow them to work on multiple pieces of data at once. So we can see this on some examples here. So here, in my first example, I was just going to add together 8 numbers. I couldn't use 8 here because the compiler was just optimizing this away. And you can compare this to using the vector class, where we create 2 vectors of 4 numbers, so 4 32-bit integers. And then we can add together those 2 vectors. So it's the v3 at this point will contain 6, 8, 10, and 2029. We then add together each of those individual elements to give us the same result as doing that. And okay, if we're just doing it for 8 numbers, this add will be lots quicker because it's trivial. But when you've got 10,000 numbers, we can see that this is a quicker approach. So the question there is, well, okay, this is great for add. Can we use it for anything else? So, okay, we can. And this time I'm going to have 2 arrays, 1 to 999 and, sorry, 0 to 999 and 1 to 10,000. It doesn't really matter what the 2 arrays are. I just wanted some different numbers because the test I was going to try was, first of all, find the differences between all the sort of matching elements in those 2 arrays, and then put them into a third array, and then just sum up those differences. So that's it using the loop. And if we want to do the same thing using vectors, we use this tensor primitives class to say subtract. So we're going to subtract everything in here from there and put the results in there. And then once we've got our differences in here, we can just sum them. And on tensor primitives, there are loads of different possible operations you could do. I just picked one to try out. And we run that. And we see, wow, yeah, this tensor primitive class is a lot quicker than doing the loops, as we can see here. So in conclusion, you should use benchmark.net for measuring quick things. It's not so useful for measuring slower stuff like business applications because you don't need this level of accuracy. And you don't want to get carried away optimizing something you don't need to. Also, remember what you're measuring, because we started off measuring the speed of for loops when we've ended up measuring something completely different. So we got very sidetracked. I think it shows that you should challenge what you think you know. When I started this, I had no idea that a for loop was going to be a for each loop was going to be quicker than a for loop. Also, the core libraries are more than just abstractions. I just assumed it was just going to internally do a loop over an array, and obviously, no, it doesn't. And there's a lot more to learn about SIMD and vectorization, which was going to be the original talk, and maybe that could be a topic for a future talk.